Sorry, Jasmina. Hi, Jasmina. Sorry. Jasmina?
Hi, sorry, it didn't connect.
No,
to
it's my
audio for
fault.
some reason.
I've been trying to get your final schedule down, and I don't know whether I'm required to give you that final between the 4th and the 6th, or whether I can lop it over into the next week, which I'd rather do for you. Give you a little bit of time between tests. So I'm sorry about this. I'm sorry I was late, but that's what I was trying to do. Do you
Fine.
remember where we ended, Jasmina?
No.
Okay. Was I finished with Vesper? Did I go through polarity? Did I talk about polarity at all?
I don't remember exactly.
Okay. Gabe, you there? Gabe? 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 Gabriel? Okay. For some reason, he's not answering, Jasmina. So what I'm going to do is I'm going to go back and start with polarity. And I got through at least all the shapes, didn't I? Did I get through octahedron? Jasmina?
Yeah, I think so.
Okay. Now, if you've got a larger molecule, like this particular one here, this one has 3 central atoms in it. Okay. If they ask you what the geometry is on this molecule, you can't really answer that question. The person that's asking the question has to be more specific. Person's answering the question has to be, he has to say, do you mean the left carbon, the carbon in the center, or the right oxygen? Because this molecular structure is tetrahedron. This one is going to be trigonal planar. This one is going to be bent. Does that make sense to you?
Hey, Professor, can you hear me? Hello?
Yes, I can, Gabe.
Oh, okay, great.
Do you remember, Gabe, where we ended?
Not really. I think right here. I think right here, yeah.
Okay, so you understand that, Gabe. If somebody's asking you if you have a larger molecule and somebody's asking you what the shape is, you can't really tell them unless they specify what the center atom is. Because this one has 4 things around it. It would be tetrahedron. This has 3 clouds. This one's trigonal planar. This one has a tetrahedron electronic geometry, but a bent molecular shape. Does that make sense to you all?
Yeah.
Okay. Now, I have to get into, by the way, I'm sorry I'm a little late. I was trying to figure out what was happening with your finals.
You're fine.
I'm sorry? Yeah.
No, you're fine. You're fine.
All right. What happens is in molecules, electrons aren't always shared equally. By the way, hello, Ian. How you doing?
Not too bad. I'm at work.
Okay, good. Sorry I'm a little late. The polarity of a compound is that property which allows a molecule to orient itself when it's in a magnetic field. So if we have like one side of the molecule that's negatively charged and the other side that's positively charged, if I have a positive end of my magnet up here and my negative end down here, my molecule is going to orient itself so that the negative end is towards the positive end of the magnet. And I don't think I'm saying anything that's earth-shattering there. Now, the problem that happens is we have to have polar bonds for that to occur. In a polar bond, the electronegativity difference between the two atoms has to be between 0.5 and 2.0. If you do have that, that means the electrons are going to spend more time on one than on the other. If the electrons are over here, that means this side of the bond is negative. This side is going to be positive. Okay, now, again, all this stuff I've been through before. Now, what happens in a molecule? If I have three things, if I have two things, if I have a tug of war battle between two 250-pound men, and they're pulling with equal force, is the center of the rope going to go anywhere?
No.
So if everything is balanced, then I don't have a negative or I don't have a positive side of this molecule. Because if I have a positive up here and a negative down here, if the molecule starts to rotate this way, this negative down here is pushing the negative side away. So if I put this molecule in a magnetic field, it's not going to rotate. Does that make sense to you?
Yeah, it does.
All right. Way back in medieval times, they had this quaint little custom called drawing and quartering. And basically what they would do is they would hook up a person to 4 horses and yell, "Giddy up." Now, if the horses pulled with equal force, the torso wouldn't move. That's what's happening when we're dealing with molecular polarity. So 2 things have to happen for a molecule to be polar. The first is it has to have polar bonds, because if there's no unequal sharing of the electrons, there's no positive or negative force. The second thing is you got to look at the entire molecule. And when you look at the entire molecule, you got to kind of analyze it such that you can see that it is asymmetrical. If it is perfectly symmetrical, then like the 4 horses, they're pulling with equal and opposite force. So the molecule doesn't have an overall negative or positive side because it's evenly distributed. So you got to look at, does it have polar bonds? Is it symmetrical? If I have carbon dioxide, linear molecule, they're pulling with equal and opposite force. Because it's equal and opposite, this doesn't move in a magnetic field. It is non-polar. So you need to have bond polarity and you need to have asymmetry. So when you're determining molecular geometry and polarity, if we have something like water, water has a bent shape. The electrons congregate mostly on the oxygen and less on the hydrogens. So that means I have a negative side and I have a positive side to this molecule. This molecule is also not symmetrical. Because it's not symmetrical, water is going to be highly polar. So water itself would have a dipole moment. I'm going to show you some different molecules. Jasmina, why is HCl polar?
Because it's asymmetrical.
Because it's
asymmetrical.
Asymmetrical, and what else?
Polar bonds.
Polar bonds. Gabe, what about ammonia?
It's asymmetrical.
Asymmetrical. If you look at this, the top half of this molecule doesn't have 3 hydrogens coming out of it, does it?
Right.
So if it doesn't have the 3 hydrogens coming out of the top, it's going to be asymmetrical. Again, polar bonds. Now, if I look at carbon tetrachloride, which is in the center here, Ian, all of these things are equally spaced from one another. Ian, is this a symmetrical molecule?
Yes.
So even though this has polar bonds, it is a non-polar. So look at this one, Ian. Is this one symmetrical?
No.
Even though it has a symmetrical shape, because of the fact that you have a different atom on top, it's not a symmetrical molecule. You have a negative side and you have a positive side to this.
So would bent molecules differ then?
Bent molecules?
Yes.
Okay, we have water. Water is a bent molecule. So,
Okay.
so in the case of water, this is asymmetrical and it has a polar bond, which is a plus.
Okay, that makes sense.
Now, if I have a trigonal planar molecule like this, okay, instead of having boron in the center, what I'm going to do is I'm going to put a sulfur there and 2 oxygens down here. That sulfur has a lone pair out here. It's also bent in. Sulfur and oxygen have, they're both polar bonds.
Right.
So this is asymmetrical and it has polar bonds. If it's sulfur dioxide, it is polar. Now we have to also apply that to octahedrons. So if I have, let's go with this one. If I have a total octahedron and all the atoms are the same, is it symmetrical?
Yes.
So if it's symmetrical, that molecule will not be polar. Same instance, I have the same atoms on a square pyramid. Is this a symmetrical atom?
No.
So if it's not symmetrical and those bonds are polar, that will be a polar molecule. Gabe, how about the square planar? If all the green ones are the same atom, is that going to be polar or non-polar?
It's polar.
Gabe,
Yeah.
are these pulling in equal and opposite directions?
Yes.
Is this molecule symmetrical?
Non-polar. Yeah, non-polar. My bad.
All right. Same thing happens when we're dealing with the trigonal bipyramid. If I have the green balls are occupied by the same atom, this molecule is entirely symmetrical. It will be non-polar. If I have another in a seesaw shape, is this shape going to be symmetrical or not?
Yes.
Seesaw symmetrical. Let's look at the top here, Gabe. Is that Ian or Gabe?
Ian.
Ian, is the top half of this molecule the same as the bottom half?
Yes.
No, the top half only has an electron pair there.
Oh. But
So-
wouldn't the sides technically make it symmetrical though, because they're pulling at the same area?
But the top half of it.
Oh, it doesn't have, okay.
The top half doesn't have the balancing of all the rest. If it had
Okay.
another atom on the top, then you would be right. But since it doesn't have that atom on the top, there's nothing up here that will balance out.
Oh, okay.
Much like this, T-shaped Ian. Is this going to be symmetrical?
Yes.
Again.
Wait, no, because you're
Okay.
pulling, because it needs one on top for it to be equal. Got it.
How about this one? Linear.
That's equal.
That's equal. So you got to kind of picture these things in your mind. Seesaw and T-shaped are not symmetrical. Linear and trigonal bipyramid are. Again, the assumption I just made is that the atoms are the same. If I have a linear molecule where I have iodine in the center, iodine on one end, and fluorine on the other, that's not symmetrical. So that would have a dipole. It would be polar. Does that make sense?
Yes.
All right. So we're done with polarity. Okay. All right. Now, if we're dealing with quantum orbitals, do you remember how the p orbitals were oriented? Do you remember they were labeled px, py, and pz? Do you remember that?
Mm-hmm.
Well, if they're px, py, and pz, they're following the x, y, and z axes. What would the bond angles be? What are the bond angles between the axes in a Cartesian plane?
Would it be 30, 60, or oh wait.
What's the
would
x
it be
and a
30?
y? You have an x and a y here.
90 degrees.
90 degrees.
But
so
then Z, wouldn't it be 45?
What's that?
If it was on the Z plane, wouldn't it be a 45 degree?
Because if I'm out of the z plane, the z plane is going straight through here.
Oh,
3D.
Okay.
So if quantum mechanics worked, if quantum mechanics was a do-all end-all, then all the bond angles would be 90 degrees. So there has to be something else going on in there. Let's think of something else. I want to go slideshow on this. All right. I've drawn the orbital diagram for carbon. How many unpaired electrons does carbon have to bond with? Come on, guys. How many unpaired electrons are there in this picture?
Two.
So it can only bond with two things. Is that true?
Yes.
I have methane here. Methane has carbon. How many things are bonded to the carbon?
4.
But quantum mechanics says it can only have two. So something has to be wrong. Another thing, beryllium fluoride exists. It is out there. Sorry. But if you look at a beryllium, the orbital diagram for beryllium, beryllium has one s2, so that orbital is filled. It has two s2. Both of those electrons are filled. Can beryllium bond with anything if all it has is paired electrons?
No.
But the compound exists. So something has to be wrong with the quantum mechanic theory. So when it doesn't add up, when the theory doesn't add up, you change the theory. Everybody thought he was a stand-up character. Got one more. So what we're going to do with those atomic orbitals is we're going to hybridize them. We're going to make a tangelo from a tangerine and an orange. We're going to make a mule from a donkey and a horse. Yeah, I know it's a donkey, but let me go with that analogy anyway. What we're going to do is we're going to take those atomic orbitals and change them a little bit. We're going to blend S and P's. We're going to blend S, P's, and D's. And that's going to help to explain bond angles, and it's going to help to explain what's happening in quantum mechanics. Another cartoon. So if I have an s orbital and I have 3 p's, what happens is the shape I get gives you a big side on one, a little side on the other. Do you see that? If I blend these 2 orbitals together.
Yes.
Now, if I put all these together, right? Won't the big sides try and move as much away from each other as possible? And when they do that, they make the form of a tetrahedron. Normally speaking, when we think of covalent bonds, we basically share the electrons of adjacent atoms. So the HCl bond straight forward, I get a sharing of these electrons. And because I'm getting a sharing of these electrons, I have a bond. So when they overlap, I have to get an overlap of these orbitals so that they can share the electrons. So as I get them to the ideal state where the bond is formed, I have the lowest energy. If I try and shove them closer and closer together, the energy goes up to the point where it can't exist. If I get them further and further apart, also the energy gets lower and lower till I get to the point where they're separate atoms again. So we can see atomic orbital theory works if we're dealing with something like F2. I don't have to hybridize the orbitals because I have one free electron that can bond directly with another fluorine with one free electron, and I have a bond. So if we think about the BeF2, this molecule is known to exist. If I hybridize the atomic orbitals, I can get an appropriate electron pattern. So if beryllium looks like that, what I'm going to do is I'm going to take this 2s and I'm going to take one of the 2 p's. Now you have to understand, when I hybridize them, when I put 2 orbitals together, this is going to have an overall energy graph where the hybridized orbitals are going to be greater than the 2s, but less than the 2p. So what I have is I'm going to promote one of the electrons to the 2p, and then I am going to hybridize those 2 orbitals. And what I'm going to get is I'm going to, out of one s and one p orbital, I'm going to get 2 hybrid orbitals. It's like if you take a sandwich, slice it in 2, from each half, I get 2 new orbitals. So if I get these two hybrid orbitals, they're going to be 180 degrees apart from one another because that's as far as they can be apart from one another. Then we are going to get an overlap with an F2p and another F2p with beryllium's hybrid orbitals of sp. And that is how BeF2 can exist. Are we okay here, guys?
Kind of.
Yeah, it's
Kind
kind
of.
of confusing, but
Okay. When we absolutely need to do it, we can hybridize orbitals. Okay? in the case of boron trifluoride, okay, the boron needs 3 regions. So it needs 3 hybrid orbitals because boron only has 1 free p orbital. Boron's atomic orbital diagram would be 1s2, 2s2, 2p1. So I have to make 3 sites on boron in order for it to make BF3. I do that by promoting one of the s electrons to the 2p orbital. Then energetically, the s and the 2p's blend together, and they make a hybrid orbital that is sp2. It makes 3 of them because 3 atomic orbitals went in, 3 hybrid orbitals have to come out. So I have used 1 s, 2 p's. That makes 3 sp2 orbitals. And I also have a free p orbital that's not hybridized. So again, going back to the beryllium fluoride, what happens is the 2s orbital no longer exists. It's been hybridized with one of the p's. So I have a 2sp orbital. I have 2 2sp orbitals that are hybridized, but I still have the 2 p's that are there. So basically, what we're proposing is that we have a series of hybridized orbitals. Each is going to accommodate an electronic domain and shape. So I know this kind of sounds esoteric, but bottom line is this is simple, guys. It really is. If I need to accommodate 2 electron clouds, my hybrid orbital is going to be 2 sp hybrid orbitals with 2 p's left over. If I need 3 things, if I need 3 electron clouds around the center atom, then the center atom, the orbitals of the center atom have to be hybridized so that I use 1 s and 2 p's to make 3 sp2 orbitals and 1 free p orbital. If I have 4 electron clouds to make the tetrahedron, I have to combine s, p, 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 so I get sp3 orbitals. I get 4 sp3s because 4 atomic orbitals went into making them. At this point, I have no more free orbitals. I've used the 3 p orbitals here. If I'm going to 5, well then, I need 5 electron clouds. I need 5 atomic orbitals. S, P, 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 I'm out of p orbitals. I have to employ one of the d orbitals, and so that hybridization is sp3d. I'm going to 6. That means I need 6 atomic orbitals. S, P, 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 D, D. S, P3, D2. Is this kind of making sense?
Yes.
Kinda.
Okay. All you got to do, count the electron clouds. You're going to draw the Lewis dot structure, right? From the Lewis dot structure, you're going to have the number of electron clouds around the center atom. If I have 2 things around the center atom, I need a hybrid orbital that employs 2 atomic orbitals. So I have 1 s and 1 p. 3 things around the 3 clouds around the center atom, I'm going to need 3 hybrid orbitals. So therefore, I got to use an s and 2 p's to make my 3 sp2 orbitals. 4 things, I'm going to need 4 orbitals. spp or sp3, I'm going to have 4 of them. When I go to 5, I've got to employ a d orbital, so I make sp3d. Octahedral, 6 things, I got to employ sp3d2. So a basic question would be, I would give you NH3 and ask you, what is the hybridization of the N central atom? Because it has 4 things attached to it, the hybridization is going to be sp3. If I give you SF4, SF4, there are 5 things around an SF4. If you would draw the Lewis dot structure, the S would be bonded to the 4 fluorines. It would also have a lone pair there. So it has 5 things around the central atom. The hybridization of the sulfur is sppd. Is that making sense to you now?
Yes.
Count the things around, count the electron clouds around the central atom. That will dictate what your hybridization is. Okay, when we mix n atomic orbitals, we get n hybrid orbitals. So if we mix sp2, that's 3 atomic, we're going to get back 3 sp2 orbitals. Therefore, if I'm only using 2 p's, I've got 1 free p orbital left. And because I have large lobes, the lobes are going to orient themselves such that they're as far away from one another as possible. So sp2 hybrids have a trigonal planar geometry. sp3 tetrahedron. sp3d trigonal bipyramid. sp3d2 octahedron. Yeah. So if I'm dealing with boron, these are how I would draw the atomic orbitals for boron. The first thing you do when you're doing a hybridization orbital diagram, you promote one of the electrons. That means I have 3 sites now, 3 orbitals that can be involved in bonding. So I then would take all the orbitals that are involved in bonding, hybridize them. So all the ones that are occupied by at least 1 electron get hybridized. That means one of the S's and 2 of the P's. This energy is higher than the 2s, lower than the remaining 2p. When I have carbon, this is the atomic orbitals diagram for carbon. I promote 1, hybridize all of the orbitals with 1 electron. This gives me 4 sp3 orbitals. They're degenerative. I have a large lobe and a small lobe. They want to get as far apart from one another. So a sp3 orbital has a tetrahedron shape. And this is just same information as you already know. If I have to add a D, I'm going to get sp3d hybridization to do the trigonal pyramid. Octahedron is going to be sp3d2. Again, this last thing, that's the whole beauty of this. The electron domain geometry from Vesper is going to determine the hybridization. So if I have my promotion to give me 5 sites, I'm going to have 5 sp3d orbitals with 4 remaining 3ds. That leads to a trigonal bipyramid shape. If I have 6, that's going to lead to an octahedral. Step 1, when you're doing this, determine the Lewis structure. Determine the electron clouds around the center atom. Then determine the number and type necessary to rationalize the bonding. PCl5 has 5 clouds around the P. Therefore, I need 5 orbitals, S, P, 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 D. Are we good? We have an understanding of this.
I do.
Jasmina?
I'm good too.
Yeah, I
Dave?
do. Yeah, for the most part.
All right. The key is, though, you have to remember this. There are still some unhybridized orbitals there left. Like, for example, if I have an sp3d2, I have 3d orbitals I haven't touched yet. And your next question is going to be, is there such a thing as an sp3d3? I'm not aware of any. Yeah, this would be a good site. NCl3. 4 domains. What's the hybridization, Jasmina? Jasmina.
Sorry, for which one?
I've got 4 clouds around the nitrogen. There's a lone pair and 3 bonds to chlorine. What's the hybridization of the nitrogen in NCl3?
sp3.
Good. Ian, H2O.
That'd be sp3.
sp3. Gabe, SF4. There are 5 clouds around the sulfur.
That'd be like sp3d.
Guys, isn't this simple? It's not that hard at all, guys. And this is just another chart that shows you the hybrid orbitals, the geometry, and it gives you an example of a possible compound. All right, now we got to get into something called bonding. And there are 2 types of bonds, sigma and pi. Sigmas are head-to-head overlaps. They're the best bond. This is if you take 2 atoms and you smack them head-to-head. When you smack them head-to-head, they get a sharing of the electrons. It is the closest bond. It's the bond length is the smallest. It is the strongest bond. A pi bond. If you have 2 orbitals that are parallel to one another, you can have a pi bond. If one electron is in this one electron is in this one, basically they bond this way and you get an electron density above the internuclear axis and below it. Single bonds are always sigma bonds because the bond overlap's greater and the strength is better. If you have a multiple bond, one of the bonds is sigma, the other is going to be a pi in the terms of a double bond, or if I have a triple bond, a sigma and 2 pi bonds. Always, this is what happens all the time. If you have a single bond, that's just 1 sigma. A double bond, that's a sigma and 1 pi. A triple bond, a sigma and 2 pi bonds. Okay. When we have a molecule like formaldehyde, what we have, what is the hybridization about the carbon? How many clouds? Somebody's trying to answer and they're not being able to. How many clouds are around the carbon? Okay, Gabe, is that you that's trying to answer?
No, that's Ian.
Okay, I kind of thought it was, but I just wanted to call on you.
SP3.
Anyway. SP3, SP3, or how many things are around the carbon? How many clouds?
4. 3.
3. So that means what kind of hybridization?
SP3.
No, 3
No.
things.
Oh, SP2.
SP2. Okay. Now, is there a free p orbital, Gabe?
No. There is.
Because I've used an S and I've used 2 p's.
Oh, you're right. You're right.
So there is a free p orbital on the carbon.
Right.
That orbital is going to stick straight up in the air. It's going to be perpendicular to the trigonal planar hybridization, sp2 hybridization. Okay. Now we have our oxygen. What's the hybridization on our oxygen, Gabe? How many things are around? How many electron clouds are around the oxygen?
Oh, 1.
No.
3.
3. The
Oh,
letters each count like an electron cloud. So,
yeah.
Dave, if there are 3 things around the oxygen as well, what's the hybridization on the oxygen?
Would it also be SP2?
And does it have a free p orbital
Yes.
that sticks straight up?
Straight up in the air, perpendicular to it.
So the carbon has one sticking straight up, the oxygen has one sticking straight up, and they both have electrons in them. So you get 1 sigma that's caused by the reaction of one of the lobes of the sp2s with the other lobe, the sp2 lobe on the oxygen with the sp2 lobe on the carbon. So that has direct overlap. But you also have these p orbitals that have an electron in that cause the double bonds. Does this make sense, guys?
Yes.
Okay. In a triple bond, okay? In a triple bond, I have, sorry, I'm going to go get out of here for a second. Share screen, whiteboard. I have acetylene. Okay. What's the hybridization about both of these carbons? How many electron clouds are around the carbons?
Two.
So what's the hybridization?
SP.
SP. So I got my sigma is along the SP hybridization of this carbon and this one. Okay. Now I'm going to undo that last bit of crap that I just did in there. Now,
Professor,
yes.
I have a quick question, and I think you mentioned it earlier, but I just want to make sure. So there's 2 things around carbon, right?
Yes.
So you would write it as SP, not SP2. Why is that?
Why is that? Because you
Yeah.
have 2 atomic orbitals. All you need are 2 atomic orbitals to make 2 hybrid orbitals, Gabe.
So you wouldn't put SP2?
No, because if I had sp2, that would mean, stop that. That would mean there would be three things, three clouds that I need to account for on the carbon.
Okay. Okay. So
I'll go back to the formaldehyde and show you in a second.
Okay. Sorry about that.
No, it's no problem. Now I have an sp. It's got a big lobe. This has a big lobe and they overlap, right? They're along, and this is a linear fashion. But my carbon also has two p orbitals. So this is a p, this is a p. My other carbon also has two p orbitals. P, P. Now, if I have an electron in here and an electron in there and one in here and one in here, these two will make another bond and these two will make another bond. This is pi. This is pi. So overall, I have 1 sigma, 2 pi bonds. Always, always that way. Single bonds will always be a sigma. Double bonds will be a sigma and 1 pi. Triple bonds will be a sigma and 2 pi. The orbitals that are going to be involved in the pi bonding are going to be p orbitals, and they are going to create electron densities above and below the internuclear axes. Questions about this? Now, going back, Gabe. Let's see. I'm going to go back a slide. Are you seeing this slideshow, Gabe?
Yes, I am.
And okay, now I'm going to, no. Okay, now, Gabe, this carbon has 3 electron clouds, the double bond and the 2 single bonds. So I need 3 electron clouds around that carbon. So I have to involve, in order to make 3 hybrid orbitals, I have to involve 3 atomic orbitals. So in that case, I'm going to mix 1 s and 2 p's to make 3 sp2 orbitals. Okay, Gabe?
Okay, that makes sense.
If I have acetylene, the acetylene only has this triple bond here, so 1 electron cloud, and another bond to this hydrogen. So it has 2 electron clouds. If I have only 2 electron clouds, that means I only need to hybridize 2 atomic orbitals, s and p. Does that make sense, Gabe?
Yeah.
However many clouds you have to make, that's how many atomic orbitals you have to hybridize.
Oh, okay, I'm getting it. So if it's like C, if it's C and then there's 2 around C's, or there's 2 H's, my bad. So if there's like a C and then there's 2 H's, so that's what? 2 electron clouds. So that'd be an S and a P.
That'd be an S and a P, yes.
Okay, that
If
makes
that
sense.
molecule existed, Gabe. Carbon needs to have 4 things around it. All right. This is nothing more than I've told you already. A sigma bond is a direct overlap along an internuclear axis. When I have a double bond, that involves 1 p orbital that's free and 2 sp2 orbitals. Again, if I have a triple bond, that's going to involve, I'm sorry, this is a double bond. Again, the double bond would have a overlap that you're seeing here, and we would have an electron cloud above and below the internuclear axes. All right, if you guys are going into organic chemistry, you're going to need to know resonance and why it becomes important. Remember, if you're able to draw 2 or more Lewis structures in which you can manipulate the double and triple bonds such that you make another legitimate Lewis dot structure, what happens is you have resonance. Now, if I'm drawing this, guys, what is the hybridization about the nitrogen? Come on, guys, how many things are around the nitrogen?
3.
3 things. Now, this flips back and forth. Okay, so it goes constantly around the merry-go-round there. How many things are around this oxygen?
3.
3. Same thing with this one. Same thing with this one. So in effect, what happens is the oxygens are also sp2 hybridized. If the oxygens are sp2 hybridized, each one of the oxygens has a p orbital that's sticking straight up.
So you're basically manipulating the structure and just like moving around the bonds and calling it resonance.
Yes.
Okay.
But Gabe, you have to realize each one of these oxygens, because I can manipulate the double bond around it, each one of the oxygens is sp2 hybridized, which means it has p orbitals. Each one of them has p orbitals sticking up.
Correct. Yes.
So if it has p orbitals sticking up, the electrons can be in a cloud over here, can be in a cloud over here, can be in a cloud over here. And those electrons constantly move around so that I have a spreading out of the electron density over the entire molecule. Go back. Okay. Does that make sense to you, Gabe?
Yeah, it makes sense.
If I spread the electrons out over a bigger force, bigger area, this makes the molecule much more stable. If I have benzene, there's nothing that's special about these 2 carbons that's any greater than these 2. So that double bond can be flipped over here, which would flip this one down there, which would flip this one over there. Now, how many things are around each carbon? How many
4.
electron clouds?
4.
Ian?
4.
Double bonds count the same as single bonds, right?
Never. Okay, so 3.
3. So what's the hybridization of each one of these carbons? If you have 3 clouds, how many atomic orbitals do you need?
3.
sp2. Do I have a free pi? Do I have a free p orbital?
Yes.
So each one of these carbons has a free p orbital sticking up. If that's the case, then the electrons can go back and forth, and I have an electron cloud above this molecule and below it. When we're dealing with resonance, the pi electrons are delocalized. In other words, they can be spread over the entire structure. Sigma bonds can't do that because they have a direct overlap. And they must maintain the basic structure. Let's see, where am I? Sorry, I'm want to make sure I'm saying everything I need to say. So when we have that delocalization, there's a spreading of the electrons all over the entire molecule, and that makes this benzene structure very, very stable. When I have nitrate, that's going to be spread over this entire molecule so that it's going to look like this. And again, these are nothing more than what I've already explained. Okay. Now I got to get through molecular orbital theory. We have a new phenomenon. O2 is paramagnetic. A paramagnetic molecule has unpaired electrons. If the unpaired electrons of the atom bonded, they would be all paired. In the Lewis dot structure, as well as valence bond theory, all of the electrons in O2 appear to be paired. So we have to figure out, if I have one oxygen mixed with another oxygen, basically the two P's would overlap and I would have all the electrons paired. The other thing, right now we can't predict whether double and triple bonds will exist. So we have to go through a new phenomena. Stop. Gracie. Stop. Okay, paramagnetic is the property of a molecule that's attracted to a magnetic field. In order to be paramagnetic, you need to have unpaired electrons. Diamagnetic means that it's not attracted to a magnetic field. All the electrons are paired up. So if I have something that is all paired up, it's not going to affect the weight of this. If I have an attraction or a repulsion, that will indicate a paramagnetism or diamagnetism. So we need to figure out another bonding theory. So what we're going to do is we're going to create molecular orbitals rather than hybrid or atomic orbitals. And in the molecular orbitals, you have to understand that the orbitals are the property of the entire molecule. They're similar to atomic and hybrid orbitals. They have specific shapes and energies. Each orbital can accommodate 2 electrons each. They fill according to the Pauli and Hund rule, and the number of molecular orbitals equals the number of orbitals that are combined. So if I have a hydrogen, if I have a constructive combination of 2 orbitals, that means that the electrons happen to be in the same space where the 2 orbitals can overlap. What happens if the electrons are on opposite sides? Instead of being here, What happens if they're over here and over here? No electrons are in the center, so there can't be a bond. So when we have the destructive bond, the electrons are over here, and there's an actual separation between the two hydrogen atoms. The constructive look to make the bonds, the destructive look to destroy the bonds. So again, we're dealing with the internuclear axis. So if it's straight on, this is going to be a sigma molecular orbital. If I have the bonds that are destructive, that's going to be a sigma star 1s. And what the star means is that is considered to be an antibonding molecular orbital. So if I just have the plain sigma 1s, this is a bonding molecular orbital. I put the star up there, that's an antibonding. So what I am doing with this is I am combining two atomic orbitals. From that, I am going to make two molecular orbitals. One is going to be a bonding orbital that's signified by a sigma 1s. That has less energy than the original atomic orbitals. The antibonding is going to have more energy than the bonding will. Again, I have started off with two atomic orbitals. I've made two molecular orbitals. I have two electrons. So by Hund's rule and Pauli's exclusion principle, they go into the orbital with the less amount of energy. So they both go into the sigma 1s bonding orbital. Now, are all the electrons paired? I got to go back here and make sure. Okay, 1 second. Let me, I know I'm going back and forth here, guys. Getting back to paramagnetic and
Every
diamagnetic.
element, or
We're not talking elements, Ian. Right now, we're talking molecules because we're talking molecular orbitals. Paramagnetic needs unpaired electrons. Diamagnetic, no electrons are unpaired.
I think I meant to word it like, so does this only work on certain molecules?
I'm only going to hold you to the first line of the
Okay.
periodic table.
Okay.
After that, it starts to get real complicated. Okay, Ian?
Got it.
So I'm only going to hold you to hydrogen through neon. All right? Are we okay with this so far? Again, we're talking about a new theory. The amount of atomic orbitals in equal the molecular orbitals out. The molecular orbitals are designated by if it's a head-to-head reaction, those orbitals will be called sigmas. If it's going to be a side-to-side, those will be called pi's. So I have a sigma, damn it, I have a sigma bonding and a sigma antibonding. Again, just like all the other orbital theories, they get into the lowest energy level first. So they get put into the lowest energy level. So there are none in the anti-bonding. So what this tells me is that because I have more bonding than anti-bonding, that this molecule will exist. It's also telling me that with both of them in the same orbital, I have paired electrons. It is going to be diamagnetic. So rules: atomic orbitals in equal molecular orbitals out. They follow Hund's rule and Pauli exclusion. And the bonding only occurs when there's an energy advantage. And that's what we're talking about here. An energy advantage is when the electrons in the bonding orbitals are greater than the electrons in the anti-bonding orbitals. And we can determine that through the formula called a bond order, which is electrons in the bonding orbitals minus the electrons in the anti-bonding orbitals divided by 2 is going to be your bond order. If the bond order is 0, this means bonding orbitals, electrons, and non-anti-bonding orbital electrons are equal. If that's the case, no bond can happen. If the bonding exceed the anti-bonding, then you have the molecule. So if I have hydrogen, I've got 2 in the bonding, none in the anti-bonding, 2 divided by 2, I have 1. It's a stable molecule. If I go with helium, again, helium has a 1s atomic. If I have 2 of these atoms together, each of them has a 1s atomic orbital. I make a sigma 1s bonding, a sigma 1s anti-bonding. I fill the electrons up. I get bonding electrons 2 minus anti-bonding 2. I get 0/2. I get a bond order of 0. H2 is not a stable molecule. It does not exist. Okay, I'm going to stop here right now. I need something from you guys. I got to make up one lecture because you guys are one lecture behind the other class. Literally speaking, this is where I ended on last Thursday for the other class. So you're either going to have to make this up by looking at the videos, or you're going to have to make it up by agreeing to meet with me at some other time. Which would you prefer?
I can watch the other video and then just join the 5:30 Zoom call to make it easier for me. But I don't know about everybody else.
That's fine, Ian. Gabe and Jasmina, what would you prefer?
I think I'll watch the videos.
Okay, because I am not going to be able to get you through. I'm not going to be able to get you through the next chapter. I need 2 sessions to do that.
What chapter is it again?
It's the
14?
chapter on intermolecular forces.
Okay.
Jasmina? I'm willing to meet you one-on-one, either one of you, at a separate time.
I like Zoom calls, but if I'm not sure when I'll be able to do it because I'm going to St. Augustine for a few days. So
I understand, Jasmina. Believe me, I understand. I'm going to Lighthouse Point tomorrow, so I know what you're talking about. I'm sorry about this, but for some reason or other, I'm just proceeding a little slower in the morning session than I am the evening.
yeah, it's okay. I can watch the videos.
Okay, and you have the evening Zoom class as well as the videos that are on the online outline. The other thing is, guys, You have to understand, I'm just going to proceed on. I'm going to start here on next Tuesday. Okay? I'm going to start here on next Tuesday, and I'm going to go as far as I can. And
So
you'll
the
just be
ex-
responsible for making up the rest of chapter 12.
So the exam isn't this week?
No.
Oh.
Ian, how can it be?
I didn't really
Thursday's
think that one
Thanksgiving.
through. Yeah, my bad.
The
Okay, well,
exam
that's-
is going to be on, I believe it's the 3rd,
Next Thursday.
next
Then.
Thursday.
Okay, that's easy then.
All right. So the exam,
So
is,
if sorry.
the exam is going to be on December 3rd. Okay.
Okay, so if we watch Thursday's evening Zoom, we'll be caught up for the 5:30 class tonight.
If you watch tonight, Ian,
Uh-huh.
if you watch tonight's 5:30 and next Tuesday's 5:30, you will be
Okay.
caught up.
Okay, I'll
right.
join the 5:30 then for sure.
Also, there's a little more of this molecular orbital theory that's going to be going on. Okay. Other thing, would you prefer? Right now, I may be forced into giving you the final on the weekend of December 4th. So that means I would open up your exam from the 4th through the 6th. I may be forced into that. I would prefer leaving it for the 7th through the 9th. What would you prefer?
It doesn't matter to me. I'm fine with whichever.
Okay.
I can make whichever one work, whatever's easiest for you, Professor.
I literally was hoping to get you at least a little break between the 4th test and the final. But for some silly reason, they made the online classes finals from the 4th through the 6th. So I may be forced into doing that.
It's fine.
Okay. I'll determine the evening class what they determine, and I'll try and do my best, or I may not have the option.
all right.
Okay,
Yeah, you do
guys.
whatever's easiest for you. We're fine.
How are you guys doing with the stuff you had today? I realized this molecular orbital was thrown at you at the last second. How are you doing with hybridization, polarity? Does it seem to make sense to you?
Yeah.
Kinda, yeah.
All right.
It's slow at first, but you understand it after you explain it, and we get a couple examples of it.
Okay. I just want to make sure that you're kind of on solid ground with this stuff. Because what I am going to do is I am going to go through the first. Oh, sorry, wrong direction. I am going to go through, this is the first row of the periodic table. And I will have you responsible for the first row, okay?
Got it.
Other than that, I'm not going to get into it. Okay, so I have literally 1, 2, 3 slides to go. Had I known that, I would have gone for it. We'll start here on Tuesday then, okay?
Okay.
Sounds good. Thank you, Professor.
Take care and get to your classes that you need to get to.
Have a great Thanksgiving.
You have a great Thanksgiving yourselves.
Thank you.
Thank you for mentioning that, Ian.
I got another question too.
I'm here.
Okay, so is this for the exam, is it the same thing for the lab class with the dates? Final?
No. That has already been determined. I think I already let you know on that.
That was on the Zoom call?
That is going to be on next Monday through Wednesday.
Oh, okay.
Okay.
How much of the last lab will be on that exam?
There will be a question.
Vaporization? Okay.
Generally speaking, Ian, generally speaking, there I think are 14 labs that you've gone through this semester. Pretty much assume it's going to be one question from each lab.
Okay. I got to go through that Zoom call again for heat of vaporization. I don't know why, but that didn't click with me at all.
Okay. Can you stay after or? Do you have to go
Yeah, I
somewhere?
can stay. I'm at work, so I can stay.
I'm glad is your boss fine with this?
Yeah, I work at a group home company, so I kind of have a chillax schedule. So I'm able to
Jasmina,
do this when I need to.
Jasmina, you good?
Yeah, I'm good, I think.
Okay. All right, Ian, I'm going to get off of this and I'm going to stop sharing here.
Okay. I don't
And I'm going
have
to get onto the whiteboard.
I don't have any of my notes with me or my lab paper. I just got copy paper in front of me.
Okay. Let's say, all right, you have, let's not do that. 400 torr pressure. And by the way, I thoroughly expect you guys to screw up the math on this.
Okay, yeah, because yeah.
And
My
this is gonna
numbers
be-
were nowhere near right.
It's the math that's doing you in.
Yeah.
You have 400 torr pressure at minus 50 degrees Celsius.
Okay.
Okay. And again, this may be an absolute absurd model. What temperature does it boil at? Okay.
Okay.
I said it's boiling. What's the pressure?
760.
760. It's atmospheric pressure. I also have to give you one more bit of information.
Mm-hmm.
Gracie, stop. Stop.
Would that or ATM, is that the same as Tor?
No.
Okay.
It's not the same as torr because torr is 760 torr is equal to 1 atmosphere.
Okay. Okay.
Delta heat of vaporization is equal to 6.50. There are a couple things that you can do wrong with here. This is a point.
Okay.
All right. So the overall formula, Ln P1 over P2 is equal to negative delta H vape divided by R times 1 over T1 minus 1 over T2.
I think I already see where I went wrong. I don't think I divided by R. I think I might have multiplied by R. Because isn't R 6.184?
8.314.
Okay. It's a constant, right?
Yes.
Yeah, I definitely multiplied by the constant when doing the lab.
Okay.
Oh, quick question since I brought that up. Is the lab book due next Sunday or was it due last Sunday?
Don't worry about it. Just submit something, Ian.
Well, the Dropbox closed. It's one of those drop boxes that ends and closes on that date and time. And it was marked.
I will try and open it for you, Ian.
Okay.
Don't worry about it. It's not going to be overly. It's not.
Yeah, I figured that.
At this point, Ian, the way he did this is screwy as hell. He gave you 9 points for each of those lab notebooks, and there were 14 of them, which gave you
an excess.
The lab notebook is supposed to be worth 100 points, and if you multiply 9 times 14, this gets you 126 points. So you have 26 extra points in there.
So almost 3 lab books extra.
Yes.
Okay. Got it.
All right. Now, you got the Ln of, all right. Here's something you have to understand with this particular equation.
Right.
You can put P2 over P1. But if you do that, you have to change the T1 to T2 minus T1.
Which is which? That's another thing I was confused on. Like, how do you decipher
it doesn't
which
matter.
one? Okay.
It doesn't matter. If you put the 400 there, the key is the T1 has to go, the temperature associated with that pressure has to go in the first position.
Oh, okay.
And the temperature that you're, or the pressure you're dividing by has to be associated with the temperature in the second position.
Got it.
Okay. So in order to get this to Kelvin, I have to add 273 to that, or I have to subtract 50 because it's minus 50. So this is going to be equal to 223, right?
Mm-hmm.
Now, R is 8.314. But it is joules.
So you
per
got to
mole
times
K.
it by it.
So you either have to do one of two things. You either have to multiply this by 1,000 or you have to divide that by 1,000. Okay?
Oh, okay.
So that's another part that gets people screwed up. A, it is not associating, not putting the T's and the P's in the right places. And the other thing that screws up is you don't multiply this by 1,000 or divide that by 1,000.
I think I multiplied the 6.5 by 1,000, but then I didn't divide by the R value. I multiplied by the R value. I believe that's why I went wrong.
Okay. If you, well, you can stay in here as long as you want.
No, I still will for sure.
Okay. So this is going to be 6,500. Divided by 8.3. Times 1 over 223 minus 1 over T2. All right, now I got to do some math here. ln of 0.526 is equal to 782 negative 782 times point I hate drawing 8s on this thing. Minus 1 over T2. Okay, now you have to make sure you're not hitting the log button, that you're hitting the natural log button.
Right.
So I got negative 0.626 is equal to, I'm going to have to multiply this by that. Although this is a point.
Yeah.
And that is a negative 350. And then this becomes a plus 782 divided by T2. .88 is equal to 782. Again, this is going to be an absurd number. Divided by T2.
Mm-hmm.
T2 is equal to 200. Oh, it's not such a bad number. 271. Now, another thing that occurred, if you look at this problem that was on the post lab, it asked for temperature in degrees Celsius. So at that point, you had to subtract 271. So it's going to be T2 is equal to a -2 Celsius. Okay.
Mm-hmm.
Now, just a couple pratfalls on this. Again, key is associating the right pressure with the right position of the temperature.
Okay.
That's absolutely key. Second thing, making sure that you're either multiplying the delta H by 1,000 or dividing the R by 1,000. Third thing involves messing around with the logs. Make sure you use the ln rather than the log.
Got it.
You got this down?
Yeah, that makes a lot more sense than what I managed to do last night.
Okay, I'm going to throw something else up here now.
Okay.
Another problem that happens. Say you're asked for the pressure rather than the temperature.
Okay. Will one pressure always be 760?
More than likely. It doesn't have to be. It does not have to be. But more than likely with these problems,
Got it.
I'm just going to multiply this out already. Divided by 8.13. I'm tired of writing numbers. Times 1 over. All right. We're going to call this 250.
Okay.
Minus, might as well use water or something like that. 1 over, nah, maybe not that. 298. Okay.
Okay.
Now, when you're doing this, you have to realize that this is the ln of x over 760. All right, Ian? It is not the ln of x divided by 760. Do you see the difference there?
Mm-hmm.
Because I have people straight out the bat, what they do is they multiply this next number by 760.
Right.
All right. 6820 divided by 8.314, 820 times 1 divided by 250. Point 00336. Okay, so I got the ln x over 760. They had to teach classes in this. Now, this number is bigger than this number. So my overall number here is going to be negative. And that means that my pressure here is going to be smaller than 760. Now, here's where people run into the problem, Ian. What they do is they multiply the negative 0.524 by 760. Okay?
Right.
And that is the wrong, you can't do that. What you have to do right now is you have to take e raised to the x over 760. This is how you solve logs.
Oh, I used that wrong too. Because I flip-flopped the ln to the other side and I did e to the power.
No.
Okay.
This is how you have to solve this. Okay, I'm sorry, e to the ln. Now, what you have to understand, and we'll put it up here, e raised to the ln x is equal to x. That's why we're doing that.
Okay.
Okay, so e raised to that ln x over 760 is just equal to x over 760. Now what you do is you take your E button.
Right.
This is equal to 0.524, 592 rather. Now you multiply it by the 760. And actually this turns out to be a pretty good problem. 450. Again, this is key. You have to understand this part when you're dealing with logs. So that you raise both sides e to the power, and that eliminates this as 1.
Okay.
Okay?
Got it. That makes a lot of sense now.
Again, part of the problem of my teaching chemistry is I also have to teach math.
Right.
So, and literally speaking, how much time have you ever spent on logs in your life?
Not a lot.
So that information is flittered away.
Right. And you're relearning it and all that.
Does this help?
Yeah, a heck of a lot, yeah.
Okay, anything else I can do for you?
No, that's it. I'll see you at 5:30.
Okay.
Have a good one, Professor.
Yeah, are you doing okay with this though, Ian? The stuff I went over today.
Yeah, I'm understanding it. I'm gonna go watch the last couple Zoom videos to study and understand it, like the last chapter for sure. But it's definitely sticking a lot easier than before.
You also had, were you at the 5:30 on Tuesday or not?
Last week, yes.
No, on
Thursday I wasn't.
This past Tuesday.
I think
this is
so.
Tuesday today, is it? Thursday, last Thursday is what I meant.
No, I was not.
Okay, then good enough, because I got through this on the lecture on Thursday.
Okay. I'll probably go back and rewatch that one while I'm at work, just so I can get caught up.
Good enough.
So, all right. See you at 5:30, Professor.
See you at 5:30.